Okay. So good afternoon, everyone, and welcome to our IPARCO seminar. Today, I'm pleased to introduce Dr. Mainak Singha. Mainak received his PhD in astrophysics from the University of Manitoba in 2023, where he was mentored by Professor Stav Baum and Christopher Odia. His doctoral work emphasized the multi-wavelength study of black hole feedback, utilizing IPU spectroscopy across optical, infrared, and millimeter wavelengths. He has extensive experience with the high-resolution imaging data, HST and Chandra, and radio interferometry. Currently, he's focused on producing realistic spectral simulation for the Roman Space Telescope's wide-field instrument using both the GRISM and the PRISM. His work aims to enhance our understanding of black hole formation and their role in cosmic reionization. Today, Mainak will present on the topic the hidden cosmic titans, unveiling low-luminosity AGN in Reionization-Era Analogs. Thank you very much, Mainak. The floor is yours.
All right, thank you so much, Enrique, for the nice introduction. So hi everyone, I'm Mainak. Today, the talk will be primarily focusing on uncovering the low luminosity AGN, which might be massive or intermediate mass black holes in the local universe, or that are also similar to reionization-era dwarf galaxies. But also at the second half, I'd also talk about the future NASA flagship missions, for example, the Roman Space Telescope and the Habitable World Observatory, and their role in improve our understanding on how the black holes and the dwarf galaxies contribute to the reionization quantitatively. So to start with, what's the reionization? So after the Big Bang, 380,000 years later, the universe rapidly cooled and expanded, and the electrons and protons combined together to create the neutral hydrogen. So the neutral hydrogen wouldn't let any low energy photons pass through, but that was the case till redshift about 2030-ish, called the cosmic dark age, as the first stars started to form, also called the Wolf-3 stars, which are very massive and short-lived. They started to create copious amount of high energy ultraviolet radiation, and the radiation was powerful enough to got through the shroud of neutral hydrogen and slowly start to ionize the universe. Theorists believe that this process went till the redshift 10, when we had the first galaxies forming and starting to ionize the universe even more. So about at redshift 10, the universe was expected to be ionized by just 10%. Slowly, when you have the first black holes and the galaxies and the stars start combine all their radiation, the universe gradually became even more ionized, and at redshift 7 or 8, when the reionization was accelerated, the universe slowly got more ionized, even reached at 50%. And we believe that the reionization was mostly complete by redshift 5.3. And then obviously, then you see an abundance of massive galaxies, quasars. So what was the process? So the first stars, the first galaxies, when they started producing the ultraviolet radiation, they started to create ionizing bubbles of ionizing bubbles or radiation bubbles. Those bubbles started to expand and grow, and these bubbles started to overlap and merge together and filling the universe with ionizing radiation, and basically cutting through the neutral hydrogen. Now, this depends on the source size. The bubbles may be different. When you have a massive galaxy or have a very massive black holes, that may create a really huge bubble because it has a very powerful source inside. Whereas for the dwarf galaxy, that's where the sizes are much tinier. They might create a much, the bubble up much lower sizes. But also it depends on how many of those are at each redshift. If you have a decent number of dwarf galaxies, that could produce the bubbles of like mini tiny bubbles that could also drive the ionization. But we don't really know like what's happening without like really digging into like that redshift, and where obviously you need highly sensitive observation, for example, JWST. So in the after JWST got launched in 2022, in over the last 2 years almost, there have been like many works, and the results been quite contradictory, I'd say, because in 2015, like that was like much prior to the JWST launch, Pierre Madot's group, they wrote a paper that like quasars could possibly dominate the entire ionization because they're like so much efficient in producing the ionizing photons. In 2019, a group from Harvard, Smithsonian, and Cambridge, they suggested that the reionization could be mostly dominated by massive galaxies with the stellar mass exceeding 10 to the 8 solar mass. Also, they're called the oligarchs. And recently, that was in 2024, you see the top the top panel. There's a Nature paper that came out that's suggesting that the most of the ionizing photons is produced by dwarf galaxies. Now, that's a problem. Like we are having a one single instrument and different people analyzing different data and getting to different results. So like what's really going on? Is there any way you could actually understand like what's contributing to the reionization? Or like we just keep on gonna, keep on just fighting and getting to different conclusions. But there's another stupendous development with JWST, that the rise of faint supermassive black holes beyond redshift 4. So primarily, it was believed that the supermassive black holes population is very scarce at high redshift. So I remember I was talking to Fabio Baccucci last year at Goddard when he came visited. He said that like maybe at redshift 9 or 10, you might find only 1 or 2 black holes. Like because like as per like the theory, the population you'd expect is very low and close to zero. But now the reason after we see like what JWST showed, like we're finding them on almost everywhere. So you could see it here from redshift 5 to redshift 11. Like they are like we're just finding this massive black holes but almost every week with JWST. Like either they are radial out, their black hole masses exceeding 10 to a 7 solar mass. Sometimes their volumetric luminosity by like 10 to 40 4 to 10 to 45 Earths per second, like fairly luminous AGN. And these are obviously the famous little red dots. So like as if like they're everywhere. But like what's the implication? If you have a higher number density of black holes, they could produce a huge amount of radiation and could also slowly drive the reionization process themselves. But if that's the case, why don't we just do the entire reionization physics at high redshift and forget the low redshift? The simple answer is we just really cannot underestimate the ionizing radiation leakage beyond redshift 3. The reason is the neutral hydrogen is the biggest problem. As the redshift goes up, the neutral hydrogen column density goes up, means that like it just absorbs more and more ionizing radiation. Beyond redshift 3, we just cannot directly measure the ionizing radiation escape anymore. So if we really want to understand like how a presence of a black hole drives the ionizing radiation leakage, we have to stick to the low redshift. Does it mean that like everything is over? Because like those are high redshift, and we can get the ionizing radiation leakage fraction at low redshift. So how to solve this issue? Thankfully, we do have the analogs of this high redshift or redshift more than 6 dwarf galaxies still living among us. They call the green peas. So our group wrote a paper in 2023 before I started here my postdoc at Goddard that the rest frame optical spectra, upper redshift less than 0.5 green pea galaxies, which you see in the top panel, is very similar to a dwarf galaxy more at redshift more than redshift 8. I think it was 8.1. That was found by James Webb nearest spectral. So you can see like how remarkably similar the spectra are. So as if these are like a living fossil still like in the local universe. And these sources, not only like they have the rest frame optical spectra similar, they had their stellar masses are also very similar, like 10^7 to 10^8, 10^8 solar masses, and they are like also low metallicity. They have like a really high specific star formation rate. So they're like everything is similar. So these are probably the best analogs again of the high redshift universe that we can find in the local universe. And the advantage, we could literally point out all our high resolution instruments, for example, Hubble, James Webb, Muse, radio interferometer, even ALMA, like, and see like what was the radiative processes that's going on, and that trigger the Lyman that ionizing radiation escape. So just like a bit more like about the green piece, what I was saying that like these are subsolar metallicity, and these are also like very compact, like UV half-light radius, like 330 parsec. So it means that we could only resolve these sources with like Muse narrow field mode, JWST, um, and on so something that could get under like point like 0.1 arc-second resolution. Because like with Muse we have like a 1 arc-second resolution, but like Muse really cannot like resolve these sources. These are like ultra compact. But sometimes we do see like these sources are like packing within 330 parsec 10^8 solar masses and having a black hole of 10^7 solar mass. So like these are like really spectacular sources. And just to imagine like these things were living at the high redshift universe, like it's remarkable. Like to understand like how these galaxies form and how they grow is itself like really interesting. And the fact that they're in the low redshift is basically that like a golden opportunity to understand the reionization in the local universe laboratory. So the general consensus before 2022 was these green peas are mostly star forming galaxies with there's like no AGN population. So why is that? They're like the green peas were first discovered in 2009. But then the catalog slowly grew larger and larger. But all the BPT diagram, whenever you find them, like they're always residing in the star formation locus of BPT. There's like literally nothing in the liner, nothing in the AGN. And also, uh, even if you like look for the X-ray emissions, like most of the times they were like all very consistent with like star forming models. But in 2021, there's a paper by Harish et al. That saw a mid-infrared variability in this green piece. So the fact that this is like the mid-infrared is not obscured by dust, and you do see like a variability that itself suggests there's like a probably a non-thermal source residing, or maybe which might be a massive black hole. And in 2023, we wrote a paper in MNRES. We did actually found that like once we do the spectroscopic deep blending, the emission lines, oxygen H beta and nitrogen 2 H alpha, they are actually in the AGN regime. Not only that, but they're also dual agents. So we see like two distinct narrow peaks with the black holes masses being like 10^7 to 10^8 solar mass. And sometimes their bolometric luminosity reaching about 10^47 arc-second. Like these are like extremely luminous. But the host galaxy sizes, these are like less than 1 kiloparsec, and their stellar mass is like 10^10 solar mass. So I still don't understand like how in this universe this could be possible, but this is like simply like way too interesting, and we really need to get high resolution observation to understand like how this universe can actually form such objects within like such a small scale. But so far we had like 2 black holes with medium infrared variability possible and 4 with optical emission line diagnostics. But this is just not enough. If you really want to understand the impact of these sources in terms of a cosmic reionization, we need to see if there are more sources, because if their density is like low, it means nothing. Okay, there are like somehow 6 black holes were formed, but it doesn't mean anything for cosmic reionization. So our strategy was to go to the entire Chandra archive and the X-ray data archive and see what are the sources that has X-ray observation. And why is that? Because a good way to check for the existence of an AGN or like massive black hole is that if the X-ray luminosity is more than 10 to the 42 hours per second, you could safely rule out all the starburst processes like ultra-luminous X-ray sources, and you have to invoke a massive black hole's existence. But there is a problem. There is sometimes called the low luminosity AGN, where the X-ray luminosity could be as low as 10 to the 38 hours per second sometimes. But the problem is, if you reduce that threshold, you're going to also be confused by a lot of like X-ray binaries, neutron stars, super-Eddington accretors, that could also give rise to the similar X-ray luminosity. But how to tackle this problem? So the optical emission lines, aka the high ionization lines, which is like helium-2 and the H alpha, if we have those information, thankfully we do have from the Sloan spectroscopic data, we can combine these 3 pieces of information to actually constrain the origin of the X-ray emission and to really pinpoint if there's a massive black hole or not. So what we did, so we started first modeling. So from the Chandra X-ray archive, we had out of 29 sources, we had the observation, but unfortunately, there was like only for 9 we had X-ray detections. We didn't have for the 20, like there was like no X-ray emission was detected. But for those 9 sources, what we do see that like all of them have high ionization lines, helium-2 and H alpha. And the H alpha couldn't be fit with the single component. We had to invoke a broad component. But this is not like a broadline region typical, but it's like a much more narrower. But obviously, there's like a broad base we do see in H alpha. Whereas for helium-2, that's a peculiar line because we do have iron-3 and argon-4, iron-3 4658 and argon-4 4710. But you do see that like helium on the left panel, how broad the helium-2 is. Like for this galaxy, the full width of max about almost 1200 kilometers per second, whereas for the other 2 lines is like much narrower. So you do already see that like the helium-2 and H alpha line widths are not really similar. And basically we do find like a range of line width of helium-2 throughout our sources. So it's time to really combine all the informations and see what are the what's the source of the X-ray emission. So first thing first is to check if these are X-ray binaries. A good way to check is if you divide the X-ray luminosity with star formation rate, and if your population is dominated by an X-ray binary population, you'd expect the specific X-ray luminosity, the star formation, the normalized X-ray luminosity to be to have like a negative anti-correlation with the Merrill-Listi values. So what we see, we don't really see a proper anti-correlation, but but the thing is, like, we just also cannot rule it out, because for 5 sources, the statistics will be like much worse. So the answer was, we cannot tell if it's dominated by X-ray binaries or not. Now, when we talk about X-ray binaries, what kind of X-ray binaries? So the low mass X-ray binary is gonna have like much more negligible X-ray contributions. So we can just safely keep them on the sideline. For the high mass X-ray binaries, the ultra luminous X-ray source is probably the main contributor. So what is an ultra luminous X-ray source? That is a highly accreting stellar mass black holes or a neutron star. But how do we know, like, if that source is present? So when the source is highly accreting or at a super-Eddington regime, they launches a disk wind, and the wind manifests as the very similar velocity dispersion for H alpha and helium-2. So basically, long story short, if we see like a almost one-to-one correlation between H alpha and helium-2 line width, we have a super-Eddington accretor or a ULX, and then yeah, you don't need to have any massive black holes. And that's, you can see from like the blue points of the right panel that like that's is a very much case for like previous super-Eddington accretors. But when we do the same thing for our sources, we found almost like zero correlation for between the helium and H alpha line widths, and you do see like how different these are. So what's the moral of the story? That like the sources we have are really not like super-Eddington accretors. They might be something other than that. Another question would be, how about fast radiative shocks from supernovae? They could also like create like X-ray emission. But yeah, so if we start from the assumption that like the X-rays produced by supernovae, but then using a correlation by Zhang 21, we do actually show that the observed X-ray luminosity is at least order of magnitude higher than what you'd expect from any kind of supernova related processes. And someone could also ask, how about like massive stars? Then we also show that the average X-ray luminosity you would expect from massive star, aka Wolf-Rayet stars, is basically 5 orders of magnitude less than what we see. So stellar processes, we could basically safely rule them out. We also ruled out any super-Eddington ultraluminous X-ray sources. The referee, when we submitted a paper, was asking us like, how about any other non-ULX high mass X-ray binary? So what we found that if there are like high mass X-ray binaries whose X-ray luminosity less than 10 to the 39 per second, they would only contribute to 15% in the total X-ray 2 to 10 kb X-ray luminosity. So like that's like not much. It's basically about like a 1/6 of what we see. And low mass X-ray binaries, their contribution is like much less than like 1%. So you need to have a massive black hole to produce these X-ray luminosities. So what I'm gonna go back here. So you remember, like, we had the broad H alpha. So one of my collaborators suggested me, like, why don't you use these to estimate the black hole masses? Because like this may be like come from like a broad line region, and you could actually get like single epoch black hole mass estimation. So we got the numbers, and the black hole masses turn out to be like 10 to the 4 to 10 to the 6 solar mass black holes. So these are not your typical supermassive black holes or like a quasars, but they are like much more on the intermediate mass black hole regime. Now, surprisingly, these intermediate mass black holes have been like thought to be like one of the key contributor in the cosmic reionization, also called the low luminosity AGN. And the fact that previous studies didn't find them at higher redshift because their X-ray luminosity upper limit, they had like a 10 to a 43 hours per second. But like, as we see, like this is like a much lower. So like you cannot like detect like much fainter sources with a shallow exposure at like high redshift. So we need like deeper X-ray observations to actually uncover like this low luminosity AGN population. So I want to talk about what we could do in for the future missions for these sources. The fact that like we are now finding this low luminosity AGN, we really need to understand like what are their how common, how frequent these are in the local universe, so we can actually get some kind of volume density, and then slowly to use that to understand how much of the ionizing budget this could actually contribute into. So the Nancy Grace Roman Space Telescope will be launched hopefully in 2026 with like field of view 20.28 square degrees and like a 6.5 sigma detection limit 10^16 hours per centimeter per second. This is ideal for nearby galaxies. So from my calculations, Roman will detect like 1 million green peas, which is like a 1,000 time increase more than like what we have. So currently we have just like a 1,000 sources. Roman will just basically threefold the number. Well, I mean, thousandfold the number, which is like absolutely incredible because the statistic we'll get would vastly improve our knowledge on how these galaxies actually impact the environment, create the ionizing photons, and how the reionization progresses. And then using that, we could also understand how the black hole forms at high redshift universe, and how the black hole evolution goes, and how the feedback regulate the black hole growth, and also regulate like the reionization processes. The key science we are developing right now here at Goddard is like we want to constrain the black hole models, because like at high redshift you do see like that direct colors heavy seed black holes, which are at like 10 to 8 solar masses, and they're assuming like a 10 to the 4 solar mass initial seed. But now we are seeing the black hole masses to be like much more lighter, like from the analog galaxies. So are these like completely like different processes? We need like really like a high number of galaxies with like which host these massive black holes to really understand like how the black hole formation really work, like, and what environment triggers this kind of different mechanism, like what environment that triggers like a high like heavy seed versus light seed versus gravitational runaway. And then also we could use develop some kind of indirect diagnostics to really understand the ionizing radiation escape beyond redshift 3. So there has to be some sort of a correlation which we could use in the local universe, develop in the local universe, and then extrapolate that at the high redshift. So that's why like the statistics like really uh, necessary. And then obviously the number of sources will also help us understand like how the energetic output in the reionization evolved over the redshift from like redshift 10 to 11 to like redshift 6, whether they are constant, whether the black hole was dominating at some point, or vice versa. Like the Romans depth and the field of view would give us like hopefully a lot of the answers. But this is just a statistics. To understand all the microphysics, we need high angular resolution. So now you probably have heard that like NASA's aiming for the next flagship mission is called the Habitable Observatory, that to be launched in 2040s. So we created created all the science case groups in which we have like the AGN and ionizing radiation science groups. So what we came up with that to understand how did like the intergalactic medium and the first source of radiation evolve from the cosmic dawn to the epoch of reionization, and do the experiment in the low redshift. So whatever I was talking to you, this was from all like a 1D spectra, but we really need the spatially resolved view to understand which of our hypothesis is real. So I feel spectroscopy is absolutely necessary, because we need the spatially resolved kinematics to see like in which region the feedback is prevalent from the stars, from the black holes, and how they're impacting the ISM and triggering the ionizing radiation leakage. So not just spatially resolved like Hubble or JWST image, we need the spatially resolved spectroscopy. And what it could tell us, because one of the leading candidate for ionizing radiation leakage is, or the hypothesis you could say, the turbulence from the feedback. So the turbulence increases the porosity in the medium and create like the ionizing radiation leakage. So a recent paper by Marin et al. Have found an H alpha outflows line width versus the ionizing radiation leakage fraction. So if that's true, it means that like when you see like a broad, like a outflowing gas component, and you take that their line width, that would mean that the inner ISM in that region is very porous, and that's triggering like enhanced Lyman Continuum or like ionizing radiation leakage. So with the IPO spectroscopy, we can actually spatially resolve and create the maps of this wind component, and could probably and also understand if the ionizing radiation leakage fraction is actually higher in that region. So that will actually give us for the first time the insight behind like the physics of the reionization. So this is all the science. Like, what are our requirements? So state of the art, we only have the leakage fraction, the ionizing radiation escape fraction per 100 sources. We hope that like incremental progress when we like twofold the sample, the substantial progress will be made when we go for like 5 times the state of the art sample will be like 500, and major progress will be when we go for like an order of magnitude like 1000. And that's like to have like the escape fraction, the ionizing radiation escape fraction. And we obviously want to go for as high resolution as possible to understand like how the feedback or the radiation interact with this environment and triggers the radiation leakage from like parsec scale to kiloparsec scale. So we're requesting right now for the major breakthrough would be a 12 millisecond resolution, but thankfully I'm hearing that like with HWO we might even get down to 5 millisecond resolution. So like it will be like much like twice, like probably almost like 3 times better than like what we're asking in our breakthrough cases. So obviously like a lot more exciting science to come, like with the spectacular resolution. And there's been like a lot of debates going on whether you want to go for like a multi-object spectroscopy or IFU. But IFU, if you use like both for like a large amount of time, they would almost give you like a similar result. But I'm probably biased with IFU spectroscopy because it's just and also for multi-object spectroscopy, we heard like the resolution is a little lower, but the fact that we need the high angular resolution, I think like IFU spectroscopy is probably the right answer to cover the UV, optical, and near infrared, and to basically probe like the small scale to like larger scale gas dynamics, the temperature, then the density, and how all they evolve with each of these processes from across like different wavelengths. So for the instrumental resolution for the wavelength coverage, we are hoping for the first UV wavelength for like 9215, and then for the far ultraviolet, and then slowly expanding that to like 400 to cover the entire ultraviolet range, so that we can understand what's the blue light like, if there's like any significant stellar contribution in the cosmic reionization. So yeah, once we get down to like that 5 millisecond resolution and probe the entire ultraviolet range, the near ultraviolet and far ultraviolet, we think we can actually give a definite answer to like how like the cosmic reionization happened in the local universe. So yeah, this is like my concluding slides. The takeaways is like X-ray emission from our green piece of sample does have like a non-stellar origin, and this cannot be like produced by like a super-Eddington equators. and we need massive black holes. Now, the future missions like the Roman Space Telescope and the Habitable gonna combine the statistics and high angular resolution to give like all the answers we need to understand the cosmic reionization. So yeah, thank you so much for having me, and I'm happy to take any questions.
Thank you very much, Mainak, for the interesting talk, for the very nice new results. So we have time for question now. You can unmute your microphone and ask the question if you want. Well, if not, I have a couple of questions. Well, the first one is just a curiosity. When you show the result you obtain for the helium-2 line, and as we know, this could be due from the presence of a Wolf-Rayet star or the presence of the AGN. So there is an interesting diagram. I don't know if you could check. This is a kind of a BPT diagram. Instead of using the oxygen tree line over the H-beta flux from Shirazi and Tozzi, and they use basically the ratio between the helium-2 line over the H-beta. I was wondering if you did this check.
Yeah, we did. So, I mean, we have people working, that's the same, not serious biologists, but like we have like Chris Richardson, like and Kristen Garofoli, they have like used this diagram before, and we're actually having this conversation. So what we found that like they have their low luminosity AGN grid, and all of the sources at the BPT diagram, helium-2 over H-beta, and I think oxygen-3, they do lie on the helium-2 and the not like the exact Sept regime, but on that black hole masses for like 10 to about 4 solar masses at like a low ionization and low metallicity regime of that BPT diagram, because they have like different kind of locus. But the problem was they were not super sure about using that diagram, because sometimes the helium-2 is broad, and their argument was, no, you can only use the narrow helium-2. You cannot use the broad helium-2. That's not nebular emission. So I think the best way to go for it is like go for like a X shooter. It's probably and get like the high spectral resolution to like get the nebular component, and then redo the entire thing to we do the BPT diagram and see like whether we could actually find them at the AGN location. I think that's probably the best way to go.
Okay, thank you. Any other questions? Well, I also I have another question.
Go ahead.
These sources are stronger oxygen-3 emitters. So I was wondering how are their spectra in the oxygen when you look at the oxygen-3 line? If you can see the presence of a broad component, or you just see a narrow line.
No, that's a very good question. That was one of the most peculiar thing we had was in oxygen H-beta, we just only had a narrow component. If you look into my paper in the appendix, there's like literally no broad component. But that's weird, right? Because if there's like a broad component in H alpha, if that's really a broad component, you'd expect the same thing in H beta. But maybe like one of my speculation is H beta is like much fainter than H alpha. Maybe from that reason, you don't see the broad component from a black hole. But if that was the wind, I would expect oxygen to have like a broader wing component, like a blue shifted component as well, but we don't see it there. But yeah, it's weird because the H alpha and N2 has some residuals, but when I try to like, and same as oxygen H beta, but when I try to like fit another component, the fit just goes like, it just it just doesn't converge anymore. So I think that's one of the reason it is worth like following up with like something like X shooter to like get a very good quality spectra.
Okay, nice, thank you. and neither the presence of any radio jet in these sources is present.
We do have so the paper, when I was showing like the PPT diagram of all of the sources, they had NVSS data, and obviously NVSS is probably not the best data to have, but we do see a radio excess in those sources, like a strong radio excess. So maybe at some point we're thinking of putting together like a Merlin. I don't even know like where to start with, whether to go for VLA or Merlin, but I think it's worth going for the high resolution optical spectroscopy and radio observations to really see if we could actually discriminate between a nuclear star cluster, because those will be here, there, right? So we have to be careful, but also the kind of extended radio jetted component or not.
Yeah.
So maybe something to like
could be nice to investigate.
Yeah.
So if there are no more questions.
I saw a hand.
Well, Shane, we have a question. Go ahead, Shane.
Well, just to follow up on this nice point about radio observations. So possibly also LOFAR has this kind of northern hemisphere sky survey ongoing, and it's probably the most sensitive survey in the northern hemisphere to date. And in principle, it can get resolutions, angular resolutions of 0.3 arc seconds for a particular target if it's in a convenient enough location. And publicly available is like 25% of the sky. It's like a data release 2 of this LOFAR 2-meter sky survey. So you could already maybe search to see if there's some overlap with this LOFAR survey, but that eventually it will cover the whole northern hemisphere.
Yeah, 0.3 arc second I think should be fine, because like that's about Roman resolution we'll get there, right? Yeah, I think that'll already give us some ideas if there is any radio access, and obviously that'll be like much better than what we had from FIRST or NVSS. So it's worth doing it. But what I'm also trying to see that, like, sometimes when I talk to the radio community, people say, how about a star cluster? So I was kind of debating myself whether I should like start from like something, for example, VLA LOFAR, or just directly go to EVN.
Yeah, so with LOFAR, there is nice studies of the brightness temperature of particular regions, and so there will be a paper, I guess, separating AGN and star-forming components solely on the brightness temperature from the radio observations. So I think it's a pretty neat.
Oh yeah, that's absolutely. You mentioned a good point here. Like the brightness temperature would be like would be a key factor. Because like for star forming, I don't think we'd expect more than 10 to the 4 Kelvin, right, for the brightness temperature. So if we see
maybe 10 to the 5 or 10 to the 5, something like this.
So if we find something more than 10 to the 5 Kelvin, so that would be very interesting to see, because we have 1,000 sources, right? So far, to be real, we have like 15 AGN. If the number like drastically increases, like that would be like a really good sample for like future follow-up using LOFAR. Yeah, so yeah, I'm absolutely looking forward to it, actually.
So if there are no more questions, I think let's thank Mainak again. Thank you very much for joining us. And thank you very much to everybody for joining our seminar. So thank you. Bye.
Thanks for having me. Bye.
Thank you. Bye.
Thank you. Bye-bye.